I'd like to talk about what you would have for a typical op-amp circuit. In fact, this is a classic inverting amplifier op-amp circuit. But I want to think about this circuit in realizing that it actually is a sort of linear circuit where this effectively describes a voltage-controlled voltage source. And to kind of think about what does this look like, and in some ways this also helps you get a sense of what are the limits and what are the various trade-offs when we look at various op-amp circuits like this. So coming into this, I'm at least starting with the assumption you've at least seen maybe a circuit like this before. You've seen an inverting op-amp circuit with an R1 and R2 in the feedback loop. And you might actually know that the gain of this circuit would be R2 over R1, and it's an inverting gain amplifier. Okay, that starts off the conversation. But then the question becomes, well, now imagine what I'm going to have if let's say, this gain is, like 100,000. Now, a lot of times we like to assume that an op-amp is an infinite gain. And in an infinite gain, that usually means that these plus and minus terminals are identically equal. If the gain is a little less, then they're not going to be quite that. And remember that the terminals are kind of like equal or near equal, not because there's like some magic or some weird magic things that go on here that say, oh yeah, we're just going to make these be equal but not connected. It is kind of cool that you get that effect, but where does it come from? It comes from the fact that if I have a small voltage between these two terminals, the output voltage, will be gained up by a very large amount. That output voltage has to stay within the power supplies of this amplifier. It's not just like self-powered. It has to actually have supplies to it. So we're often talking about things at a signal level. Therefore, what is really important is if this voltage has to stay within, say, a plus or minus 5 power supply or a 0 to 5 power supply, the gain of 10,000, that means these two terminals are going to be within, within 100 microvolts of each other, which is often very, very small. And so as a result, you can think of these being relatively equal to each other. But that being said, let's actually look at the analysis and see what happens. And one of the things that you notice here is that we can take this circuit and it basically turns into this very straightforward circuit with a voltage-controlled voltage source. Now I flipped the terminals minus to plus because the core sort of moving variable is the minus terminal, so I want to make sure I capture that. And I want to keep my signs as positive as possible. It's always good to be positive, so I just go with that. And so I have the output voltage here, input, you have the two resistors across the string, and then it's this intermediate node here from here to ground that I'm calling V1. And so we're going to want to figure out what does that look like. And although I won't solve for it explicitly here, you could actually take all these values and say, well, how big is V1? And once you get the output voltage, you kind of know that V1 has to be 10,000 or 100,000 smaller than whatever V out is. And so all this stuff still sort of follows the same conversation we had. Okay, so what we can immediately say is V out, since it's connected to a voltage source, it's pretty straightforward. It's got to be minus A sub B V1, again, because it's the opposite sign. And then I write KCL here at V1. Well, if I do that, I result in this equation. Well, a little bit of manipulation with this equation, and then putting V1 in here, gives me an equation for Vn, where I get V out on this side, and then I get the term here for V out, which has actually V out over A sub V. Okay, so you can see that the V1 term would have came from here, over the parallel combination of R1 and R2. And so you start from there and you go, wait, I've got V out and V in. So now I just need to do a little bit of algebra. And after working through the algebra, I get V out over Vn is equal to minus R2 over R1 times 1 over 1 plus an interesting term that's related to that particular gain. So if it turned out that the actual values here would have been, and here, which would be, if you kind of look at the results of this, you realize that, the ratio down here is going to be an R2 over R1. And you get kind of an interesting response here. What you end up finding is that this tends to be small, and it tends to be a very small quantity. And as a result for this term, that this is small, it comes back to sort of the ideal case of R2R over R1. As a result, and so this is what you get. And of course you can calculate that if you have two resistors, R1 and R2, you get a gain of like minus 10 out of this. you can actually put this into the rest of the expression and realize that, the resulting error of the solution is actually pretty small. So it turns out not to be too much of a big deal. And so as a result, you can kind of see and work through these calculations that things are pretty straightforward. And but it's really interesting to be able to see what happens when you talk about this as a finite gain and what that result would actually look like.